Hello and welcome. In this video, we're going to take a look at the derivative of one of our favorite functions in calculus, which is e to the x, the natural exponential function. Now, it does have a great result when we're all done with finding out what the derivative of it is, but it's not exactly easy to compute. And now with this video, hopefully you'll also understand kind of what the significance of this number e actually is. So let's dive in because it's not immediately obvious. The natural exponential function is the function f of x equals e to the x, and you can see its graph here on the right. Keep in mind that it always passes through the point at 0, 1. So what is the derivative of e to the x? Well, the first time you're ever trying to compute the derivative of a function, we always need to go back to the limit definition of that derivative. The derivative of a function is the limit as h goes to 0 of the function evaluated at x plus h, so e to the x plus h, minus the function evaluated at x, all divided by h. Okay, well, we've done this kind of thing before with polynomials, and we have some tricks up our sleeve, such as expanding things out, collecting terms, and factoring and canceling. But we don't have a polynomial. Well, we've got some other tricks up our sleeve with radicals, and if we have roots, then sometimes we need to multiply by the conjugate, expand, simplify, cancel, but we don't have roots either. And we've also seen some tricks with limit definitions of the derivative with rational expressions where we need to get a common fraction, common denominator, simplify, and cancel. But again, none of these strategies really work this way. So we have to start thinking about rules of exponents. And e to the x plus h, whenever we have two exponents added together, we can always simplify. Remember that a to the b plus c can be written as a to the b times a to the c. And e is simply just a number like any other. So we can write this as e to the x times e to the h minus e to the x over h. And now we can start to see that a few things are able to factor. Well, we could factor e to the x out, but it doesn't seem like anything actually cancels here. What's a little bit trickier is the fact that this factor of e to the x, well, we tend to think about x as our variable. But in the scenario where we're looking at a limit, the only thing that we're really trying to plug in here is the value of h. And h we're trying to get closer to 0. But x is nothing to do with h. E to the x can be thought of just like a constant. Since we're not changing e, that's just the number, we're not changing x either, since the only value we're varying here is h. So this e to the x, that is actually treated like a constant here. And that can be moved out front of the limit because of the constant multiple rule for limits. So what does that leave us with? The limit as h approaches 0 of e to the h minus 1 divided by h. Well, you can start to try to think about this logically, rationally here and justify your answer. But it's a little bit tricky because e to the h, as h goes to 0, gets closer and closer to 1. And 1 minus 1 in the numerator is going to get closer to 0. But that isn't enough information. Just the fact that the numerator goes to 0 doesn't tell us enough yet. Let's take a look at the denominator. The denominator is just h. And h is also getting closer to 0. So the value of the numerator and the denominator are both getting infinitely small, but that is leaving us completely clueless as to what the value approaches as they both become small. We could try a little numerical approach here and see what kind of result we might get by just plugging in some numbers of h close to 0. Don't forget, this is a two-sided limit. We should try values of h close to 0 on both the negative and positive sides of 0. It might make sense to make a table and try a table here of values of just slightly bigger than 0 and tables just slightly less than 0, approaching 0 from both the positive and the negative sides. And plug these in and see what you can compute for the value of e to the h minus 1 over h. Now I'm just going to cheat and get Maple to do this for me, but you could do this on any basic calculator. Okay, none of these turn out to be very great numbers, but we can start to see a pattern. the numbers coming in of 0.1, 0.01, and 0.001 will give us values slowly approaching the number 1. And from the left-hand side, choosing values of h just slightly to the negative side of 0 will also see us getting values getting closer to 1. In fact, the number e is developed or designed so that this limit does equal 1. That's really just the whole purpose of what the number e is so great with, is that this limit e to the h minus 1 all over h as h goes to 0 approaches 1. Now, all of that will allow us to evaluate this limit, the limit here in blue. That value appears to be just equal to 1, so as a result, we just have e to the x as the derivative of e to the x. Or simply, it's e to the x times 1, and that's the derivative of e to the x. So we end up with just the nicest possible rule here, the exponential rule. The exponential rule says whenever we differentiate e to the x is its own derivative. Now, it probably sounds a bit strange to say that, but here's what it actually means. We can go right back up here to this graph now and think about the slope of a tangent line at any given point. So, at the point 0, 1, if we plug in 0 into this function, we get a y-coordinate of 1. And as a result, the slope of this tangent line is also equal to the value e to the 0, which is 1. So at that coordinate 0, 1, we have a slope m equals 1. Here's another point. If we go ahead and plug in an x equal to 1, then our point on the graph is 1 comma e, which is a roughly 2.718. And at that particular point, the slope of the graph is exactly e, or roughly 2.718. Whatever the y-coordinate is on the graph of y equals e to the x, its rate of change is equal to the y-coordinate. So whatever the y-coordinate happens to be is also the slope of the tangent line. It does make a little bit of sense when you think about exponential growth. The larger the value, the faster it's growing. And that's the idea of exponential growth. Now we can combine this with the remaining rules of differentiation. And that allows us to combine e to the x with other polynomials. But this is definitely one of our favorite rules. The derivative of e to the x is simply e to the x. And e was designed so that that would be the case. Now, put all this together, you can start forming all kinds of interesting functions with x's and e to the x's, powers of x. But be careful. This doesn't say anything so far about the derivative of a function like 5 to the x. It's not quite as nice as e to the x, unfortunately. We'll see that in a future video. And we're going to have some real big problems when we start multiplying things. We haven't quite got there yet. A simple function like x times e to the x has a much more difficult derivative than you think. So sticking to addition and subtraction, there's a lot of functions we can look at, but we're not done yet. We've got lots more derivative rules. So stay tuned. I'll see you guys in the next video. Thanks for watching.